So in class, we proved theorem 2.14, which provided us with our first uncountable set. Specifically, we showed that if A is the set of all sequences x sub n whose terms x sub n are all digits between 0 and 9, so for each n, x sub n is either 0, 1, 2, 3, 4, and so on up to 9, not ending, we said, in a tail of 9s, then A is uncountable. Alright, so that was interesting because, as I said, it provided us with an example of an uncountable set, but, as we'll see now, it also shows us that the set of all real numbers is uncountable. Note that we'll talk in more detail about the real numbers very soon, but for now it's worth observing that this theorem actually shows that the real numbers are uncountable. So to see this, first note that if x is any real number between 0 and 1, then you won't be surprised to know that x has a unique decimal expansion. In other words, we can write x as 0.x1, x2, and so on through x sub n, where x sub n is a sequence in A, and this is where A is the set of sequences from theorem 2.14. In other words, that means that each of these x sub n's, so x1, x2, and so on, is a digit between 0 and 9, and in order to obtain this unique decimal expansion, we don't want this sequence to end in a tail of 9s. So, for example, 1/2. Well, that's a real number between 0 and 1, and its unique decimal expansion would be 0.500, and so on. What about another one? Well, 1/4 would be 0.25, and a bunch of zeros. How about something else? How about pi minus 3? And that would be something like 0.14159, and so on like that. We might want to note that the reason we don't want our x sub n's to end in a tail of 9s is that 0.1999 and so on is actually the same number as 0.2000, and that is exactly the reason why when we were defining our A in theorem 2.14, we didn't want any of our x sub n's to end in a tail of 9s, precisely so that we could use that set in this little remark here. Okay, so from all this, what do we know? Well, we can now say that the function f, defined from A into a set of all real numbers between 0 and 1, that takes a sequence x sub n in our set A to the real number with decimal expansion 0.x1, x2, x3, and so on, is both onto and 1-to-1. right? It's onto because if you give me any number in 0, 1, we said that it is going to have a decimal expansion, x1, 0.x1, x2, x3, and so on, where the x sub n's are in a. And it's 1 to 1 because we said that any number between 0 and 1 is going to have a unique decimal expansion. So that means if you give me two distinct sequences x sub n and a, well, the corresponding decimal expansions, in other words, f evaluated at that element of a, of those elements at a, are going to be distinct. Okay, so it's also 1 to 1. That is, f is a bijection. Well, what does that mean? That means that a and 0, 1 are equivalent. But by theorem 2.14, our set A is not countable, so the open interval 0, 1 of real numbers is also uncountable, right? If this one were countable, or at most countable, so would A be, and A is not. Okay, so hence A is equivalent to 0, 1, and therefore the open interval 0, 1 is uncountable. But I know that the open interval 0, 1 is a subset of the set of all real numbers. So R also is uncountable. Why is that? Well, if R were countable, then we know that any infinite subset of a countable set is also going to be countable. So 0, 1 would have to be countable if R were countable, but a 0, 1 is not countable, so R can't be countable either. So what have we established? Well, we've established, at least up to our understanding of the reals, we've established that the real numbers are uncountable. So theorem, the set of real numbers R is uncountable. So that is a fact that we will use. As a final comment, let's just note again that we haven't actually formally introduced the real numbers yet, but given that we are talking about countability and uncountability, it seemed most appropriate to talk about the uncountability of the reals at this point. Beginning next class, we are going to start developing the ideas needed to talk about the real numbers carefully, and within, say, 2 or 3 classes, you will be able to take a look, at this statement here, or this remark here in Rudin 1.22 decimals, where an explanation is given for why every real number has a unique decimal expansion. All right, that's all.